Very good to welcome Therese Graversen. She has spent time in the UK. She got her PhD at Oxford in 2014. She worked on statistical and computational methodology for the analysis of forensic DNA mixtures with artifacts. And she first studied at the University of Copenhagen, and after her PhD went back to Copenhagen, but moved a couple of years ago to the IT University of Copenhagen in a department of computer science. And she's the head of study program for a very interesting bachelor in data science, which I discovered quite a lot about in November, and working very hard at bringing together the sometimes disparate views of computer science, mathematics, statistics, and social sciences in that degree. And so it's very good to have her talking to us about how we actually identify individuals when actually things are rather complicated in life as opposed to in the exercises we give our students, and the samples may be quite mixed. So I guess, Teresa, a few people might join, but as Lutz says, over to you, and people will in any case join silently.
Great. Thanks for the introduction. So I will skip this. So also thanks for inviting me to speak here. So I'll try to take you through kind of the past decade of research seen from kind of what have I been up to through my perspective. So this started roughly with my PhD in Oxford, where I joined already existing efforts on DNA identification between Julia Motera here on the committee, Stefan Lauritsen and Robert Cowell. And I've also then done casework in the UK. So I want to give a bit of perspective here. So just to quickly set the scene, I'm not going to talk about DNA, but what I'll talk about today is exclusively STR marker systems. So a DNA profile for a person is, in my case here, 16 of these kind of images, so 16 measurements on a person's DNA. Either you have two different so-called alleles, or you have two of the same allele, in which case you see this kind of peak that is twice as high. So this would be a typical perfect, say, reference sample. So like if I take a swab directly from a person, I can perfectly read off the DNA profile. So where statisticians come into the picture is mostly this kind of thing, where you have a mixed sample, or somehow more complex sample. But let me talk about mixed sample, because this is like the core of my research. So here I have a mixture. Say I've mixed it of 70% from person 1 and 30% DNA from person 2. Then again, I will have something that corresponds to 2 bars of height 70 for the first person. They have allele 1 and 2, and then 2 smaller bars placed for the other person. And here you see that the signal basically gets mixed, the bars stack. So of course, in a case, I wouldn't be so lucky as to know neither that there are 2 people, nor that there are, the mixture ratio here is 70 to 30. So I just get the black signal, 16 little images of these black signals, and I have to somehow infer whatever is necessary in the case. So I'll give you a bit of context here for this. Here's a case I was involved in with the South Yorkshire Police. So in this, there was, I don't know if it was a burglary, but there was a vulnerable guy living in the ground floor of a house, and he was battered to death. And the police got hold of, in this case, these 2 men. And Nathan Fenton to the right was wearing a set of jogging bottoms where there was a blood spatter on. And this blood spatter was a mixed sample of DNA. So while I say this is blood, it was also mixed in with other sources of DNA, other fluids, I don't know. But it was a mixed sample of DNA. and the police hoped that the victim's blood or victim's DNA was somehow present in this DNA sample. So the question for me here from the police was, would DNA from the victim, Stephen Fredwell, be present in the blood sample from Nathan Fenton jogging bottoms? And this is then translated to technical terms like this. There are several ways of doing it, but there are also some principles for how to translate. So it's always about somehow formulating two alternative explanations, usually called propositions, sometimes hypotheses that sort of resonates well with statisticians. But they are really two alternative explanations of how this DNA sample came about. So in this case, I'm interested in assessing whether there was DNA from Mr. Fredwell. So I formulate one hypothesis. You can think of it as the prosecutor's hypothesis, that his DNA was there, possibly together with some other people, and we'll call them unknown. So we acknowledge that there are 4 other people there, but they are we don't know their specific profile. Whereas for Stephen Fredwell, I have his whole DNA profile. He's been swapped and typed. Then there's the alternative explanation that always says something like the person wasn't there, and that's always formulated as there was an unknown person. Again, acknowledging that there is a person, it's just someone with an unknown profile. And unknown here, there's a lot of technical statistics involved here, or distributional assumptions. We can think of it as a person with a distribution as in the population. So here, usually the propositions in the witness statement would be a bit more elaborate. It would also be explicit here that the unknown individuals, for instance, are unrelated to each other, and also to, in this case, Stephen Fredwell. Then we want to compare these two alternative explanations, and that's done in the form of a likelihood ratio. So we evaluate how likely it is to see these data under one hypothesis compared to over the other. All right, so as a statistician, how do I think about this? Well, this is an intrinsically statistical problem to me. I have some data that I measure. This I can model. This whole system I can model. So my quest this whole time has been to introduce this kind of systematical statistical thinking that we do have as statisticians. So what I was trying to do was proposing this idea as simply saying, well, we have some data. Let's model it. What would a statistician do with new data? Okay, I would start off by writing a well-specified statistical model. So I decide what are my random variables and then write up a model. So it's clear to everyone what I'm doing. Then I kind of take the consequence of that model and operate all my following analysis within that model. So what we would do, there's a natural pipeline, I pose a model, I do some inference, let's say estimate parameters, infer various quantities that I might want, or do hypothesis testing is the natural pipeline. Inference in my case here would be somehow infer parameters and compute this likelihood ratio that is what the court wants, like as my end product in a statement. And then in any analysis, we would normally check that what we did was sound. So there's a systematic way of doing model checking, assessing that the model is suitable for the data that we're actually applying it to. This pipeline can, I was proposing that this would be brilliant to use in court cases. And I did a lot of work on this, starting from my PhD. So, I mean, it's all good and well to say, I think we should do like this, but then you also need to tell people how to do it and maybe provide the means for doing this. So I provided this whole framework for carrying them out. And by this, I mean, developed the necessary methodology, right? You need a model. So that was already a very, very good starting point of the pipeline. Julia and Stefan and Carl had already been working on a specific model for a long time. And then if I wanted to do some statistics, well, I need to develop the statistical methods for this, and I need to make sure that it runs fast enough. So develop the computational method, and then I did a specific implementation of it. That was kind of to be thought of as a proof of concept, and also my own research software. And in the DNA community, this you can kind of say that my whole bulk of work is now condensed to, oh, it's the DNAmixtures software. But actually, what I want to do is not so much talk in terms of specific softwares. What I do in all parts of my work is to try to break down the developed methodology as finely as possible. So for instance, I want to distinguish between the idea of having a statistical model and a specific one. That's like one component. Then how I want to use this model for the end result, say, compute the likelihood ratio. Then how I actually decide to compute it, and the specific software implementing it. Especially the last bit, while I have a very general framework, in making the exact implementation, I have to make some implementational decisions that limits the scope maybe a little bit, but it doesn't mean that in principle we couldn't do more things. So my claim was this makes everything as transparent as possible. And I still actually stand by this claim. So the statistical model framework can be very generally described as this. I model jointly this observable signal we get. So this is the EPG profile, so the peaks we saw on this graph, jointly with the set of configuration of the configuration of DNA profiles that I want to say something about. So in this case, there's also a condition on a specific proposition. So you might think of it as this proposition says the profiles, the context for the profiles are Mr. Stephen Fredwell and 4 unknown contributors. So then that means that these profiles have a particular distribution under this explanation, specification of the people. So there's a very generic description of the model. It naturally breaks down into 2 components as I see it. So you could say the first component here is given I know exactly what DNA, so the fully specified profiles, the actual alleles, all markers. If I know this, what is the distribution of the associated EPG I will see? So, and if you want, this is the measurement process. So I've chosen not to have the actual proposition under consideration in here because it shouldn't really be case dependent. There might be surely some parameters depending on the specific setup in the lab that day, but it's not related to my assumptions about the case. Then there is something that is an inherently case-specific component, which is given the proposition I'm currently considering, what is then the distribution of profile? Is this the fully typed or the reference profile of the victim, or is it an unknown person, and so on? All right, so if I have this joint model, then naturally I also have the likelihoods, that's the marginal distribution of the data we observe. So this is very classical statistics. Likelihood is the distribution of the data we observe. And this likelihood if you want to get it from the joint model, that's a sum over all the profiles. If these profiles have a distribution, as in the population, this is a huge sum, and we don't like this. So that sum has been the headache of many people, and usually it's handled by a set of approximations, which alleviates some of the problems with doing these computations, but still limits the practical feasibility to, well, at least when I got into this, it was sort of maybe 3, maybe 4 people, unknown persons in a mixture. Right, so I started, I don't like the idea of approximation so much, mainly because I'm thinking this makes it harder for me to justify that the results are going to be correct, right? If I introduce an approximation, I also need to have some control over how wrong it can go at the end. So if I can work exactly, then as far as possible, I'm happy. Okay, so I started off by saying, okay, we need to find a better representation rather than introducing a lot of approximations to break down this sum. And there were kind of, okay, let me go. There are kind of 3 main insights we can summarize. So this would be a whole technical talk on its own, but you will get one slide. The first thing was the big space comes from each of these, the genotypes, specifically, especially the genotype of an unknown person. So let me start by finding a good representation. So representation here, you can think of it statistically or computationally. For me, it's kind of the same. But so one good way of representing this is something that has an awful lot of independencies. I've done this in terms of Bayesian networks. That's just a specification. Of course, it still means that we somehow break down the space into smaller pieces. Then another insight I had here was, well, I can actually use a standard algorithm to perform all the most of the computations I need. And this standard algorithm was probability propagation. So again, this is Bayesian networks, graphical models technique. It's actually not very simple, but it in its essence, it computes a sum over the entire network. And this is exactly what I needed. And so that insight was actually not particularly tied to forensics. It's a very generic result, basically saying, well, if I want the expectation of a product, then I can get that by probability propagation. And then the third thing was, while I started off with good genotype representations, actually that wasn't quite enough to be efficient, and that's not extremely surprising, because the probability propagation, first of all, there were several genotypes that will be linked together via the mixed signal, so that introduces new dependencies. But also that probability propagation operates on junction trees and not the Bayesian network per se. So establishing a good junction tree representation made a huge difference. Also, searching for good junction trees is very, very costly. So the sort of achievements I found that I got from this was, of course, there's this specific peak height model. So that was in particular this paper, which was a discussion paper in 2014, 15, something like that. And then a lot of work that was basically, it fleshed out in the monograph that is my PhD thesis on how to get this computationally feasible. how to operate, or how to build a system with as much correctness built into it from the beginning, or let's say a framework that makes it as simple as possible to ensure correctness. So I was trying to do as many generic algorithms as possible. Also because if you want to swap one component, say the statistical model, you want to tweak a bit. Oh, now today I want degradation. You don't want to be redeveloping every single computation you ever did. So I was trying to work kind of component-wise to make sure that as much lifts as possible when I change the model. And then ultimately trying to do something that was as flexible as possible. So both that I can make new computations along the way. So whenever I develop a new statistical method, that I also have the framework to do the computations I need to actually make this model checking plot. So I was really happy with all of this, and also it caught on. I'm happy to say in many places, particularly the modeling. The modeling had already, especially the idea of using gamma models, gamma distributions for peak heights, that had already slowly been getting momentum. But after this RSS paper, this work by Lauritsen, Paula Montera really, I think, took off a lot. But then also, I mean, maybe most notably here, Euroformix, which is now being kind of spread out, also being used in the UK quite a lot. That is basically a whole research group who took this entire framework, maybe minus the computational representation, and adapted it a bit, the modeling, to their needs, but adapted the idea of model checking and so on, and made this into a standalone software. So I thought that was actually rather cool. I know that StarMix, which is also a worldwide used software, also by one of the forensic labs and forensic science providers in the UK. I know that they use some of these computational representations. At least they told me in person. Yeah. All right. So I've said that. Well, okay. There was at least this kind of theoretical impact, and I've been touting this as a statistician. I think you should do this, but is it then useful in practice? So that's the next bit I want to talk about. So how did this kind of translate into being useful for actual casework? So back in 2016, I got a case, and this was actually by via Eurofins, former LGC, where Roberto Buxolis was. They had a complex mixture. It was somehow too complex for their in-house system to handle, and then I was instructed there as an independent expert witness, and provided a statistical report there. So this case became a bit of a landmark in a few ways. For instance, by this time, peak heights information wasn't really used in casework generally. So even just the idea of or the feat of getting a peak height based calculation through as admissible evidence was actually really amazing. And then also the complexity of the mixture. This was a 5-person mixture. Again, this was too complex for instance, this Euroformix to handle. They could, at this point, I mean, even 4-person mixtures would run much longer than I did for these 5 people. And then what happened was, I think, Peter Gill. He used. Oh, he was the opponent actually on this case. And he asked my permission to then use the statistical report as this kind of exemplary model in the Society for Forensic Genetics. This has now been used for various training in the ISFG. And then since that first case, I've used then the software for several other crime cases in the UK. And it's also been used here in the Danish jurisdiction by my colleague Stefan Lauritsen. So I'll show you here what one of my, this is a page from one of my witness reports, just to show what was kind of, say, new and groundbreaking in the way of writing these kind of statements. So I actually put in a lot of statistical argumentation. Here's and also these two QQ quanti plots to show that. Well, okay, so I've evaluated these two propositions. I say that H1 has higher evidential value than H2, and the model looks fine under H1. I did a lot of scrutiny of the model to make sure that all the aspects of the mixture was like suitably captured. And then you can also see from this plot that clearly under H2, these peaks are not, this aspect I'm looking at, it's not well captured under H2. This is very much not a straight line. So the way I write these witness statements is also kind of pushing the kind of questions that we may be asked in court, right? Because I kind of show that it is possible to reason this way. So I'm also trying to push the way that this system broadly thinks. So for instance, I think that there's a lot of focus on validating softwares and methods kind of upfront, but not so much on making sure that the propositions we evaluate with the software are sound. So for instance, we might say that H1, the likelihood ratio is more than 1 billion, so H1 is much better than H2, but that doesn't mean that H1 is good in the first place. And we shouldn't judge anyone based on, like, if the proposition doesn't support their actual presence, then it doesn't matter that it's better than an even worse proposition. But also systematics checks on whether the various model assumptions are reasonable. This can be done in a very systematic way with statistics. So let me just say it. Okay, now maybe I phrase it a bit sort of as a statistician I would, but it's certainly still done somehow in the business. It's just maybe not exactly in the system. We have a very beautifully systematic way of assessing whether this quote that I have, whether what we claim to see actually match what we see in the data that I'm trying to push for. So, for instance, of course, there is an assessment to the case of hand of saying, should I use this piece of software on this particular DNA sample? But that reasoning can be based, for instance, on, oh, I think there is too much degradation compared to my empirical validations. But as a statistician, I would say, well, I can try the model, I can look at these plots, and I can see whether there is indeed too much degradation. I can do this systematically. So this is an example of another kind of check that I do. And this is created well, actually, both of these plots that I've shown is actually in the predictive framework of Philip David, which gives some really nice properties technically. But this kind of check is, do I see the peaks that I expect to see under this model? And with this specific proposition. So here's a toy example where I made a proposition. It's three known person and an unknown that's barely there. So basically this mixture is fully explained by three people. So I line up, let's just take, I read the EPG now from left to right. I line up all the peaks that I see. And whenever I reach a particular peak, I say, well, given what I've seen up until this stage, am I surprised or not by using this model for what I see in the next allelic position? And every time there's a jump up, it means I'm surprised. Okay, so this line basically, okay, jumps up and down a little bit. Of course, we expect that sometimes we're surprised, sometimes we're not. But overall, if we somehow go above these, let's say, safety lines, then we are really in the wrong. So it gives me a way of assessing where, in which way am I surprised, and are there some systematic problems or not? So here there is no problem. The model is very not surprised by anything. But here is the corresponding alternative explanation, where we can see that that there are jumps, very high jumps, upwards, meaning the model is really surprised. And I can see that every time the model is surprised, it is where I substituted person K3 by an unknown person. Well, somehow towards the end result is that overall I'm not so surprised. And a lot of analysis can go into this. I just wanted to show an example, also an example where it actually goes horribly wrong. This is the difference if I remove one unknown person. So if I try to explain the mixture with 4 people, it's okay. If I try to explain it with only 3, it's certainly not okay. I'll be way surprised to see the peaks I see. Right. So let's talk a little bit about validation. So I spend a lot of time thinking about this, and so there are many guidelines on this from the forensic science regulator, and also quite a few from the RSS over the years, and the Forensic Genetics Society also has some, and all of these guidelines, they definitely say, well, we should have a bulk of empirical experiments that somehow, let me summarize it as, cover the space of evidence that somehow we decide that then this method is validated for mixtures within this range. And then certainly we should have a test of a specific implementation. So this is like standard computer science, you would say. And then I've tried to add to what I do also the idea here of validating to data at hand. So model checking can of course also be used in terms of empirical experiments. I can say the model says I have this expected behavior, and then I can systematically check that empirical experiments respect that. But then there's also all the mathematical proofs that, let's say, I prove that my strategy for computing these things, for my implementational strategy, is correct. So that's one great step. Of course, I could still mess up the actual implementation. So I need to test both, but I can certainly split out these two components and test them kind of separately. And this kind of side note or reflection I had as a statistician, because all of this validation work kind of strikes me that it's kind of validate. I stay in advance what I want to validate for, and then it gets validated. But the reality that I've experienced is that I somehow get into these stranger cases where somehow standard methods of software fall short. And as the statistician, it's like, well, okay, I have some new data and I look at it and I somehow adapt the model so that it meets the requirements, the characteristics of the specific case. And I can do that if I have a suitably flexible model. But in a specific case, it can be a little bit hard to justify the idea. Because it might be very clear to me that, oh, if I just set these parameters, then we have this case as a special case. But arguing this can be more difficult. So far, it's been fine with all the cases. I've not had any actual resistance, but I can see how this becomes it quickly becomes a bit of a headache. And then a major part of the argumentation in my witness statements is that I'm a statistician, so I have a particular set of particular expertise. But not only that, I was also involved in all parts of the development of the software. So it's like I'm a very, very expert user, and it kind of gave me a bit of a reflection that in developing this, of course, I don't want to develop it so that kind of only I can use it or someone, you know, when it was used in Denmark, it was Stefan Lauritsen, but he was also involved in this kind of research for many years. He was my PhD supervisor. So again, at the level of absolute expert user. And there's a big difference in the idea of a statistician looking at data, analyzing it, and then something that is intended for a non-statistician expert to produce a piece of evidence using this software. And another way of putting it is there's also a huge difference in what I would do getting this kind of per case analysis. So I don't get cases all the time, but for instance, Eurofins do. So they have this high volume turnaround. And it's a different way that you analyze data if you have to churn out a number of reports per week. And it's struck me that many of these validation and accreditation documents, they're very much targeted lab use, and I constantly find myself just ever so slightly kind of falling outside of these categories. Also in the what is my operation procedure, and like what parts should I absolutely specify upfront, and what parts can I take the liberty to adjust to the case at hand. So no immediate replies here or suggestions, just the reflections I realized I've had for several years. So just towards the end, a little bit of the future here. So much of my work has so far been sponsored by the Independent Research Fund Denmark. And this month, they also decided that they would fund me going forwards. So I will soon be a not one-person group, but one person and a PhD. So that's really nice. And so what do I want to do? Roughly. So if we look at this DNA evidence a little bit more broadly, there are, very generally speaking, two main areas of DNA analysis. One is identification, which I've been talking about up until now. So this is something that talks about what are the contributors, what are the persons who gave DNA to this sample. Everything about linking specific people to one or more DNA samples. And generally, these methods and softwares, they don't allow familiar relationships. There might, I mean, some programs make some adjustments in various sorts, maybe to cover the unknown brother alternative. There are little extensions, but not very comprehensively. And there's the other prevalent area, which is kinship analysis. That is more from another perspective, which is inferring or establishing familiar relationships among a group of people or persons. And these are typically based on single source DNA samples. So if you go to your forensic science provider, chances are they have a piece of software that does familiar relationships, probably with some legacy software that will die out in the next updating of your server, and then some single source DNA samples that can be processed. So you can probably see where this is going. We kind of want to catch evidence that falls between these cracks. So one thing is, it would be nice to allow mixed samples where there are related persons involved. This is not very difficult to imagine happening. If you have a DNA sample and you want to assess whether this is from DNA from me, you see there's also DNA from another person, but you have reason to believe it's DNA from my little brother. Well, it would be not suitable to have an unknown person, because this person is related to me, but you don't have their profile. So it's like the unknown person is my unknown little brother. So you need to specify this relationship. And coming from the other side, from kinship cases, there are heaps of examples of cases that can't really be handled. For instance, if you have this kind of rape case with the early termination, so then you have a DNA scrape from the termination, and that is then a mixture of mother and fetus of nature, and you want to assess whether a particular person is dead. Dead is maybe okay. So there are many cracks that cases can easily fall through here. So it's natural to somehow build a unified framework for this, because more generally what we're doing is we try to model a whole batch of DNA sample, and some can be mixed, some can be not mixed, and then a group of people, some of which have contributed to some of these sample, and these people can be related or not. All right. So we have really good starting points for this with lots of existing research. So even just coming from what I have now, it's already very general. It's not as many softwares are right now that you can handle one DNA sample, possibly replicate analysis, but you can actually just handle a batch of DNA samples.
Therese?
Yep.
5-minute warning.
Yeah, perfect. So where I fall short here is that the framework doesn't allow relatedness among unknown contributors. So conceptually, there would be no problem, but I need a good computational specification of this. So great people have already done this effort. So this is really nice. So Julia Montero and Peter Green, I think you're here today, exploited this this modularity of the framework. You say the model specification, that the component of the model that is specifying DNA profiles, distributions, we can take that out and swap it for a more general distribution that then allows relatedness. So this is a really amazing starting point. then what is there to do? Well, this allowing relatedness generates some extra links, some dependence between people. So there will be some complexity considerations in this, a lot of extra computational challenges. Most of the computations actually lift to this more general setup, which is why there's also basically one software already that can now do much of this analysis. The Kinmix, Julia and Peter have been working. Then there's some discussion of correctness, how much of these correctness results will lift to this specification to ensure that the software could be validated. And then there's quite a bit of more modeling that is necessary. More sophisticated p-kite models should be investigated for sure, but they're also in terms of DNA profiles, there are now we get more and more loci, so many of them are also linked. So some more difficulties should thought into this. And in general here, so there are specific models, but I want to make sure that everything I do is also at a more general level. So can we push maybe a bit or guide where the general validation processes and requirements are going? That would be really amazing. Can we integrate this kind of statistical thinking systematically into all of these processes? This is quite difficult. Of course, I've been able to do it and therefore show that it's possible, but it also means that there's a quest to make this kind of statistical tools available and operational for non-statisticians. And that's not so simple. I mean, if we look at QQ plots, we have seen them in many different contexts, and we know what is roughly a straight line. How else could I sort these points so that it gives me something informative? This you cannot do, and definitely not in a high volume or high throughput situation. And then I've been working with Eurofins on actual cases, and with so this whole project is based actually on current needs of theirs. And one big problem with open source software is that validation work. So while the implementation might be openly available in many cases, the implementation work is somehow too scarce to transfer to the in-house validation. So it means that for many of these softwares, the forensic lab will need to go basically back to scratch and validate everything, which is very, very difficult when you didn't actually develop it yourselves. So the idea here would be to make all of this validation work available openly for others to use. So even if it's not used necessarily by forensic science providers, having it available to the defense experts is also highly valuable, because in the UK there is a problem right now that the software is being used, for instance, StarMix, it's super expensive. I mean, if they will even sell it to you, and this would generally not be available to the defense and to other countries where this is just not feasible to buy something like StarMix. It would also be valuable. So here ends my my story of the past 10 years.
Thank you very much. It's very inspiring to see a description of the whole process rather than just some nice mathematics or some nice applications, but to have the two things combined and a whole lot of new challenges remaining for us. Do we have any questions? I haven't had any questions coming up in the chat, I don't think. But if you want to raise your hands or just unmute yourself and speak, be very welcome to do so. So Eurofins is happy to work with you to develop the wider use of these, and presumably different countries have different systems in terms of what they make available to the defense, and therefore what needs to be transparent.
Yes, exactly. And that's also a big issue for me, of course, that I'm trying to not necessarily validate what I do for one jurisdiction. So UK operates in a very particular way. The Danish system is very, very different. So it's very centralized in Denmark. There isn't, especially for DNA analysis, there isn't as such DNA experts. I think that if you maybe object to your analysis, it will kind of go back to the same place analyzing it. Yeah, I mean, I think, of course, this will still be on me to develop these things, but it's an asset to a forensic science provider in the UK to have available these extra opportunities, right?
Oh, undoubtedly, yes, yes. Peter?
Hello, Therese. Thank you for your presentation, and thanks for the shout out for our recent work. I wonder if you'd agree with me that we're getting better and better at computing likelihood ratios to describe the weight of evidence. But what we as statisticians seem to have little traction with is the whole business of controlling the environment in which data are collected and which questions are posed to experts. And that there's, until we have proper blinding between prosecutors and forensic scientists, for example, when these mixtures are analysed, there's risks that the evidence is completely misevaluated for things that amount to being gross errors, biases, basically, in selection of data, rather than failures of a statistical model. Have you had any experience of that sort of issue?
I'm not entirely sure I agree, actually, because I think that I do get a lot of information. I do get the full data. Of course, there's someone who has analyzed it already in the lab, but the decision on like which peak heights to include or not, that's on me. And I can go back. I need to be able to go back and vouch for the entire process. Of course, there is some, okay, I mean, I do agree that there is some lack of control here. Let's say it's okay. I've seen, you know, triaging could happen, right? But I think this has not happened in my. It's on us as kind of end analysts to go back and ask the relevant questions, like which filters were used for these data. Is it appropriate? And when you write validation documents, you will need to specify basically the whole process. And it's fine to say, I don't have control over the first part of the process, but then I need to somehow justify how I decide whether this data that I input is somehow suitable for evaluation. It is still my responsibility.
Yeah.
David, I'm just giving you a bit of a time, so fairly brief question, I hope, from you. David Cahoon.
Yes, I just wondered, and I apologize if I missed it, to what extent these methods have been tested on mixtures, known mixtures of DNAs.
Not so much. No, some, but not terribly much. No, and not as in like sensitivity analysis. So that is coming slowly, but this is something that is actually inherently difficult if you're outside a lab, because the availability of data is just terrible. I can get some data that are now open source, but then they are processed in a very particular way. And up until very recently, what happens is you need to have one of the expensive softwares, typically GeneMapper, available to even load the data. It's not just expensive, but it's not actually expensive. It's actually not even possible to buy if you're not in a lab with a mainframe and whatever 50 licenses. These things are getting better now, and also with collaboration with labs. And mostly all of these collaborations, when you try to do these kind of collaboratory testing softwares against each other, these efforts tend to break down. I never quite understood why, but there has always come some political questioning from the side that then made people back out.
That's very unfortunate, isn't it?
Yes.
Yes, I agree. Perhaps we could pick up some of these questions if we have some time for discussion at the end. But I think some people might have joined us to listen to Gail. So thank you again, Therese. Extremely interesting and plenty more work for you to be doing for the next couple of decades. So thank you very much. Gail, would you like to share your slides?
Yeah.
While you're doing that, I might mention that our second speaker, Gail, has come from is at the University of Edinburgh, and she got her PhD the same year as Therese, 2014. But in Gail's case, it was in quantitative ecology in the University of Glasgow, and she's worked as a statistical consultant in quite a forensic statistics. So I look forward, Gail, to what you've got to say.
Thanks very much. Thanks very much, Jane. This is some work that Amy Wilson and Jim Smith and I have been developing, looking at Bayesian networks and chain event graphs and how they might be used successfully to evaluate very complicated activity level propositions in forensic statistics. So in this talk today, I'm going to describe some of the work that I've been doing looking at Bayesian networks and how well these networks have been used to evaluate drugs on banknote cases. So first of all, I'll give a brief description of Bayesian networks for those of you who are not aware of how they work. So this will be pretty brief. Then I'm going to introduce you to the case that we've been working on, looking at using Bayesian networks to evaluate evidence in this case. And finally, I'll introduce a new method that we've been working on with Jim Smith. So Bayesian networks are a really useful way of combining together graph theory and probability. And they're quite useful where you've got knowledge about a system, but you've got a lot of uncertainty in this system. And this uncertainty is propagated through the system to the end of your network. It's quite a good framework to model dependencies between different variables that you might know a little bit about. And these complex relationships between these variables can be easily shown in Bayesian networks. You can see here, there's a network. Imagine that you're trying to get to work and you're wondering whether you're going to encounter a traffic jam. A lot of different variables might affect whether you do encounter a traffic jam, such as whether or not it's rush hour, what the weather might be like on a particular day, whether or not there's an accident on your way to work. And some of these variables are linked to each other, and the dependencies between them and whether or not you're going to find a traffic jam can be shown by arrows between these different nodes. Different pieces of evidence can be added to the network. For example, if you start hearing sirens on your way to work, you can start thinking, oh, maybe there's been an accident. It puts the probability of an accident to be higher in this case. And if the probability of there being an accident is higher, it means you're much more likely to encounter a traffic jam. So when you're going to work, you often listen out for sirens for that reason. So Bayesian networks have got lots of different types of nodes and arcs in them, depending on the complexity of the system you're trying to show. And they've got probability assignments for each of the nodes. The nodes represent random variables in a system, and they can be either discrete or continuous, although it's much easier to deal with discrete variables. In the talk that I'm going to talk about today. I'm going to only talk about discrete variables and ignore continuous variables, but they can be used. And nodes have got probability tables associated with them, which show the different probabilities for each of the levels in your discrete variable. They also have built-in algorithms based on Bayes' theorem that can be used to compute the effects of changes in probability in one table and how that affects probabilities in other tables in your network. Bayesian networks only consist of directed acyclic graphs, which are graphs that don't have any feedback loops, and they are moved directionally from the top of the network all the way through to the child nodes at the end. And each of the probability tables that I mentioned are associated with each node. So in this example here, where each one of these nodes represents a random variable in your system, each of them are dependent on each other based on the causal dependencies represented by the arcs. And the probability tables here can be used to represent your knowledge about the truth or falsity of a particular variable. For example, in node A, representing variable A, you have either a true or a false variable, and you can put in, based on expert knowledge or some kind of evidence, what the probability is that the proposition in this node is true. You can do this for the other nodes as well. For example, in the second node here, in the B node, there will be information about both the truth and falsity of A, because the truth or falsity of B depends on A, and also the truth and falsity of B itself. In this way, you can use the network to evaluate the probability of B being true given A is true or false. And the different combinations of these probabilities can be represented in this one node using this conditional probability table. The same is also true for the nodes C and D. And the good thing about these Bayesian networks is that if you update your knowledge about the probabilities of these later nodes, the probabilities in different nodes throughout the system will also be updated according to the algorithms that are used to construct the Bayesian network. Because they're using directed acyclic graphs, Bayesian networks imply that there's conditional independence between the different variables in your Bayesian network. And they allow different scenarios to be compared and for you to compare the effect of different pieces of evidence coming into the network in different ways. So then you can understand more about how the new evidence is affecting the node of interest in your network. That means that you can update your beliefs about a given hypothesis in this network as you introduce new evidence into the system, which is really helpful in a lot of different fields. Here's an example from a medical field. So we have lots of different information about respiratory disease in the UK. For example, we know that about 15% of the UK population smokes. We know about 50 in 100,000 people have got lung cancer, about 8 in 100,000 have TB. We also have some information about the prevalence of bronchitis and the symptom of breathing difficulties. And if we've got information about this for the whole population, we also can derive some information about the system. In this example, we can understand a bit more that smoking affects someone's probability of having bronchitis and lung cancer. We know that somebody's movement patterns might affect whether or not they have TB. From this information, you can build a Bayesian network about respiratory disease in the UK. And it might look something a little like this, where we've got information about whether or not someone's been to Asia, whether or not they're a smoker, and that affects whether or not you would expect them to have tuberculosis, lung cancer, bronchitis. And finally, down here, you can include in your network some information about the data, information where you would have knowledge about a patient's illness, for example, whether or not they have a positive X-ray for TB or cancer, whether or not they have experienced difficulty breathing recently. And information about these particular nodes can be used to update the node of interest, which might be, for example, does this patient have TB or cancer? We can also populate the probability tables associated with each one of the nodes in this Bayesian network using knowledge about respiratory clinic patients. So if we know that respiratory clinic patients are 50% smokers, for example, this can be used to update this node here. Whether they visit Asia also can be used based on respiratory clinic patient responses to a questionnaire. And then information about the prevalence of tuberculosis, lung cancer, bronchitis can also be included in networks just based on the population of respiratory clinic patients. So that means that if we've got information about the system represented in the Bayesian network, information about prevalence of different diseases and symptoms represented in the conditional probability tables, we can then use that information to decide how likely it is that a new patient coming into the respiratory clinic will have TB or cancer based on information about that patient. So we can apply that so that we've got information both coming from the system, i.e. the Bayesian network, and information about respiratory patients in general coming from what we know from the respiratory clinic. And then we can update information for a new patient based on that evidence. For example, if a new patient comes in and says that they have been to Asia recently and they have got difficulty breathing, that information, combined with the information we have for respiratory clinic patients in general, can be used to update the probability that this patient has TB or cancer. And you can see that the probability table here changes slightly in this new patient Bayesian network compared to what it did with the original respiratory clinic data. You can see that the truth of the TB or cancer node increases significantly for this patient, and that's based on the fact that they've been to Asia and they have difficulty breathing. That information is propagated back through the Bayesian network using the Bayes theorem algorithms so that this node here can be updated from that new evidence. And if you can do this for a medical example like this, you can use Bayesian networks and new information coming into them to evaluate different propositions in all sorts of other fields, including forensic science. So as you know, Bayes' theorem is used a lot in forensic science to evaluate competing hypotheses that might be put forward by the prosecution or by the defense. And the likelihood ratio measure has been used mainly as a way of evaluating the strength of the evidence, evaluating whether the evidence that's coming in is more supportive of the hypothesis put forward by the prosecution versus that put forward by the defense. And if this likelihood ratio measure is greater than 1, we can say that the hypothesis put forward by the prosecution has slightly more supportive of the evidence than the opposite situation put forward by the defense. So likelihood ratio measures are a really useful way of evaluating evidence and whether it's supportive of given hypotheses. A very simple, straightforward source-level proposition might be put forward to a forensic scientist, such as might occur in a hit-and-run case. If there's been a car involved in a hit-and-run that was recovered by the police, and on this car seat, yellow fibres were found. Nearby, a suspect wearing a yellow jumper was encountered. In this situation, a source-level proposition might be put forward by the prosecution that the suspect's pullover is the source of these recovered fibres. The defence might say the opposite, and the extent to which the evidence is supportive of the prosecution or defence can be evaluated using a likelihood ratio by examining how much and the degree to which this fibre is related to this jumper owned by the suspect. That can count as evidence and can be evaluated using a likelihood ratio. We can also build a very straightforward Bayesian network from this source-level proposition and its evidence just by connecting together the hypothesis at the top, at the start of the Bayesian network, and the evidence at the bottom, because we would expect our evidence to be updated based on what kind of hypothesis we might have. So if new evidence came into the system, i.e. if somebody did an evaluation of how much this piece of fibre matched this jumper, that would be new evidence that could be put into this Bayesian network to update what the probability of the hypothesis might be. And that's really useful, and source level propositions are really useful. The only problem is, a lot of the time they don't tell us very much about the activities of a particular suspect. A suspect's activities are a lot more interesting compared with the matching of a jumper and some fibres, although indirectly that gives you some information about activities. So forensic scientists often want to evaluate more complex propositions like activity level propositions, which are looking at the activities of a suspect and whether they were or not they were involved in a particular crime. If we go back to our example using the hit and run, the two propositions put forward by the prosecution and defence might be something like the suspect sat on the car seat versus the suspect did not sit in the car seat. Given that information, the prosecution can put forward a timeline, which might be the suspect put on a jumper, sat in the car seat of this car, committed the hit and run, and during that act of doing the hit and run and sitting in the car seat, some fibres were moved from the jumper onto the car seat, and these fibres were recovered by the police. And that's all very helpful, but when you try and build a Bayesian network, it starts to suddenly become much more complicated than the simple source level proposition Bayesian network, in that you've got information about contact, probability of contact between the jumper and the seat, then probability of transfer of the fibre from the jumper to the car seat, and then you've got information about background fibres that might be similar to the one that was found that could have been in the vicinity of the car at the time. So the question that all of this led my colleagues and I up to was, can these Bayesian networks be used effectively to evaluate these complicated activity level propositions? And the example in forensic science that we wanted to work on specifically was on a drugs on banknotes case. And Amy Wilson had been working on this a lot during her PhD, and I was helping as a consultant on the project, looking to find whether graphical methods could be used in the drugs on banknotes case that she had been working on. The idea was, perhaps with drugs on banknotes, the only evidence you often have is some contaminated used banknotes that are in the possession of a suspect. And what we want to know is this evidence of a crime involving drug trafficking? And that's a very complicated activity level proposition, because you have to infer a lot about what the suspect was doing for these notes to get contaminated with drugs. So we looked in more detail for a specific case that might be useful to evaluate. And the case that we came up with was that of Stephen Compton. The notes for this are online, so it's a real case, and we found the appeal notes, and so we were able to find out more about what actually happened. And we thought this was a good way of trying to build a Bayesian network for a complicated drugs on banknotes case. So Stephen Compton was convicted of drug trafficking, and the story of what happened was this. The police raided Stephen Compton's house, and they found in 2 safes in his house lots of used banknotes, over £100,000 in used banknotes. And of these banknotes, the police counted them on a table in Stephen Compton's house, and then they put them in tamper-evident bags and they took them away to be evaluated for drugs. And they found that these banknotes were contaminated with heroin, a lot more than you would expect from general circulation banknotes. So the police put forward the following timeline of what they thought happened during this case. They said originally the banknotes had no contamination on them, no drugs. They were just normal banknotes from general circulation, but they were taken out of general circulation by lots of different customers. These customers were all drug users, and they used heroin, and they contaminated the banknotes with their drug use. Stephen Compton came along and he sold heroin to these drug users, and he got the notes from them that were contaminated with heroin from their drug use. He then took the notes, put them in his safe in his house, and he didn't bank them because that would be suspicious. He just kept them in his house. The police found them, the police counted them on the table, and so on. So the prosecution's idea is that the contamination occurred with these drug-using customers of Stephen Compton, that implies that he was drug trafficking and implies his guilt. However, the defence for Stephen Compton put forward the following storyline. They said that Stephen Compton sold jewellery to customers. The customers were not drug users, they were just regular people. Stephen Compton innocently sold them jewellery as part of his jewellery business. Then he took the money, put it in the safe, but Stephen Compton admitted himself that he was a drug user. He used some unspecified type of drug, and he contaminated the notes himself with his drug habit. We know that he at least was using heroin, according for this to be true, but we don't know what other drugs he might have been using as well, if any. So the defence say the contamination of the notes occurred when Stephen Compton put them in the safe. He was swapping the notes around, handling them a lot, and that's where the contamination came, because he was using drugs and there were drugs in his hands. The defence also said that Stephen Compton used the table in his house a lot for his drug-using purposes, and the table became contaminated with his drugs. So when the police counted the notes on this table, contamination got onto the notes there as well through the police's counting. And you can find out more about this because the police put tamper-evident bags on the table too, so they could put the notes in the bags. And when they put the bags on the table, they would have been contaminated with drugs as well. So if there's contamination on the bags, it suggests that at least part of what the defence are saying is true. So there's two competing hypotheses, one put forward by the prosecution and another by the defence. Can we use Bayesian networks to figure out whether the evidence that we've got from this case is more supportive of the prosecution or the defence? And the main bit of evidence we have is that there's lots of drugs on these notes and there might be some drugs on the bags. We built a Bayesian network and we took into account contact between the notes and the customers, the notes and Stephen Compton and his drug-using hands, and the bags and the contaminated table. And then we also thought about putting nodes in for probability of transfer, similar to the previous networks that we looked at. In the end, there's some evidence at the end of the network, which is the amount of contamination on these notes and the amount of contamination on the tamper-evident bags. But we are missing a lot of evidence in this Bayesian network. It's very simple, but it's difficult to see exactly where we were going wrong. It didn't include some of the most important evidence in the Stephen Compton case, which is, why did Stephen Compton have so much money in his house if he was doing an innocent jewellery business? Surely he would have taken some of that and put it in the bank. That's much more likely than keeping it in his house. But we found it difficult to include that kind of evidence in the network for whatever reason. We also found it was difficult to think about the network properly because really the Stephen Compton case has got a timeline. You start off with the notes being not contaminated and then you work through that until they get contaminated by various different sources. We found that difficult to incorporate into this Bayesian network. And that's a problem with Bayesian networks in general. And they do have some problems, and it's difficult to include information that is temporal. Sometimes illogical possibilities have to be catered for, where you've got conditional probability tables in a network like this. And it's difficult to include some types of evidence. So we thought about different ways that we might model this problem, perhaps by using a timeline rather than a Bayesian network. So we went back to the start and started again. And we thought about the different propositions that might be put forward by the prosecution. And then we thought about the order that they would say different events in the Stephen Compton case happened in. And when we thought about it, there's really two things that the prosecution could argue in this case. They could argue the first hypothesis about Stephen Compton being involved in drug trafficking because he's obtaining the notes in exchange for heroin. Or it could be that he's part of a drug trafficking operation in that he was aware that there were customers involved in drug trafficking that he was selling jewelry to. He might have been involved in a drug trafficking operation whereby he sells jewelry to drug traffickers and he gets the money from them as part of a money laundering scheme. And that's another way that he could be guilty. And it's an argument that's put forward quite a lot in cases similar to this. So we thought that we would include 2 prosecution hypotheses in this Stephen Compton case. We built a timeline that accurately includes all of the events that happened in the Stephen Compton case. And each of these timelines follows the 2 different hypotheses that we postulated. First of all, on the left here, the notes are coming from general circulation. Then the prosecution say that the customers contaminate the notes because they're drug users, or because the customers are involved in drug trafficking themselves. And that follows the 2 different hypotheses. In the first one, Stephen Compton sells heroin to these customers. In the second one, he sells jewelry, but he's aware that he's part of a drug trafficking operation, and he's selling jewelry to people who are involved in drug trafficking, which implies his guilt. We did the same thing for the defense. We looked at all of the different tasks that might have happened according to the defense in this case, and we came up again with 2 different hypotheses that possibly could have occurred. First of all, that the suspect himself obtained the notes in exchange for jewelry, but he contaminated the notes with his own drug habit. Also, because of his drug habit, the police inadvertently contaminated the notes by counting them on this table. Secondly, there could be another hypothesis put forward by the defense, and this could be that the suspect was just a really unlucky guy, in that he happened to have a legitimate jewelry business going on, and he happened to go around and sell all his jewelry to people who happened to be drug traffickers, which is really unlucky, but it's something that could have happened, and so we decided to include it as a hypothesis put forward by the defense. So after we had done that, we set up a defense storyline, the same as we'd done for the prosecution, except for the defense, where we've got 2 different hypotheses. One, that the suspect and the police contaminated the notes themselves, and 2, that the suspect happened to sell jewelry to customers who had contaminated the notes because they were drug traffickers, but he didn't know about this. He didn't know that these people were drug traffickers, and it was all just bad luck. We thought about different ways to analyze this as a kind of timeline. And one obvious way was to use a staged tree. There's a picture of one here. Staged trees are often used where there's lots of different scenarios going on, and they enable you to propagate uncertainty through an uncertain system where there's complicated divides between possibilities. Here, for example, we've got bacteria on an agar plate. Either they live in a hostile or a benign environment, either there's a high amount of food or a low amount of food, either they die or survive, and you can go through every possibility in the stage tree to get to all of the different possibilities of what happened at the end. You can also do this and turn your stage tree into a chain event graph where you merge together some of the nodes that have got similar probabilities following them to make the system a bit more straightforward. So we decided to try and use these methods in the Stephen Compton case because it's a timeline similar to this bacteria example, and it might be a useful way of thinking about activities in Bayesian, rather than using Bayesian networks. So we came up with this stage tree for the Stephen Compton case. It looks complicated, but it's a lot of repetition. Imagine we're starting here at the beginning and we're saying that the notes were not contaminated. Either Stephen Compton sold jewelry or he sold heroin. If he sold jewelry, he either sold to the general public or to drug traffickers. If he sold to drug traffickers, he either knew he was selling to drug traffickers or he didn't. If he did know, he either banked the notes or he didn't. If he didn't bank the notes, then he either had lots of money as address or he did not. If he had lots of money at address, he either used heroin only or he used heroin and lots of other kinds of drugs. If he used heroin, he either had no contamination on the table was contaminated with heroin, or the table was contaminated with heroin and lots of other drugs. So this stage tree should take into account every possibility that could have occurred in the Stephen Compton case. well, obviously barring a lot of very unlikely possibilities, but assuming that these are barred, we came up with 2 prosecution hypotheses and 2 defense hypotheses. We can then merge together some of the nodes in this table that have got similar probabilities. We want to include in our chain event graph 3 main bits of evidence. First of all, we wanted to include the fact that the notes were kept at the address and that they weren't banked, which is an important bit of evidence. Secondly, we wanted to include the fact that about £100,000 of used banknotes were found, so it's not a small amount of money. And thirdly, we wanted to look at the amount of contamination of drugs on the notes, which we're going to call Y, and the contamination on the tamper-evident bags, which we call Z. The first 2 bits of evidence are incorporated as part of the storyline in the stage tree. The other bit of evidence occurs at the end of each one of the storylines, i.e. potentially you could use the amount of contamination and the type of contamination on the notes to figure out which one of the chains these notes are likely to have come from. We assumed that contamination on the notes can come from 3 main sources. Firstly, they can come from the fact that the notes were owned by drug dealers. Secondly, they can come from the fact that the notes were owned by and contaminated by Stephen Compton's own drug use. And thirdly, it could have come from contamination from the police when they counted the notes on this table. We assume that all these different sources of contamination are additive and they combine to form Y, the total amount of contamination on the notes. This is our chain event graph that we came up with. It looks complicated, but it's just roughly the same as the stage tree. At least it tries to include the same amount of information. If we start here on the left again, where there's no contamination on the banknotes, either Stephen Compton sold jewellery or he sold heroin. If he sold jewellery, he either sold to the general public or he sold to heroin traffickers. And he either knew about them being heroin traffickers or he didn't. If he didn't, there's a given probability that he banked the notes or he didn't bank the notes. And given he didn't bank the notes, there's a probability that he had a large number of notes in his house. Given this, he either was a heroin user or he used lots of other drugs. If he only used heroin, the table was either not contaminated, contaminated with heroin, or contaminated with heroin and other drugs. So each one of these chains in our chain event graphs either denotes Stephen Compton being innocent or the defence's proposition being true, or the prosecutor's proposition being true, which are all shown by these triangles. And you can see that the 3 bits of evidence are included in our chain event graphs, evidence 1 being the notes were not banked, evidence 2 being there was a large amount of money, and evidence 3 being the contamination on the notes and the bags. And these Greek letters denote event transition probabilities, i.e. the probability of each of the transitions from this node to this node, and so on. So we did this, and we found out that actually we could calculate likelihood ratios based on the results of this chain event graph. And you can do that by calculating the product of all these different probabilities that move along the chain. That means that for each one of these chains, we can calculate an overall probability of the event transitions. Then we can evaluate these by summing them up so that we get a likelihood ratio where we're comparing the probability of all the different storylines put forward by the prosecution versus all the different storylines put forward by the defence. And that way we can find out whether the chain event graph information is more supportive of the prosecution or the defence. But that's not the only information that we've got. We've also got information about contamination on the notes. So we looked at ways of incorporating contamination of the notes into this likelihood ratio. And that's what these equations here denote. Essentially, we're trying to find out what the likelihood is that would be used in this likelihood ratio calculation. And to do that, for the hypothesis put forward by the prosecution, we can calculate a weight for each of the different propositions that are put forward by the prosecution, i.e. hypothesis 1 versus hypothesis 2. And then we can look at the probability that you would find that kind of evidence given these propositions, i.e. evidence of X amount of contamination on Y or X amount of contamination on Z. And then we also incorporate the probabilities of all the different event transitions that occur in that particular storyline in our chain event graph. So using that, here's an example of how that would work in practice if you don't like looking at these equations. First of all, if we start here on the left, we would say Stephen Compton sold jewelry. He sold it to the general public. He didn't bank it. He had all this money. He used heroin only. The table was not contaminated. In this chain, you would expect the total amount of contamination of drugs on Y to be relatively low because there's no contamination coming from drug trafficking. He's only contaminating the notes with heroin, not other types of drugs, and there's no contamination on the table. Imagine the opposite situation occurs where Stephen Compton sells heroin, doesn't bank the notes. He has all this money in his house, but he uses lots of different kinds of drugs, and he gets the contamination from all these different types of drugs onto the table. In that situation, your Y contamination is going to look very different. There's going to be contamination from lots of different types of drug, for one thing, and the amount of heroin that you're going to get in the notes potentially would be much higher in contamination value because you're getting heroin from the drug trafficking customers, you're getting it from potentially his own heroin and other drug habit, and you're getting it from the amount of contamination that's on the table. So that means if we were to compare the distribution of these two different Ys, you would expect the red Y, i.e. the contamination from drug traffickers, etc., to be much higher than that of the blue Y, which would be lower, something in the realms of down in the lower end. So in that way, you can compare using the chain event graph and the evidence that you're getting of contamination on these notes. You can figure out which one of these storylines is more likely to have happened. And that's essentially what this Bayesian model we developed does, along with the chain event graph information. So we're combining together lots of different information about probabilities of all the different event transitions in the chain, together with the evidence that you might find in the notes. Can we actually fit this model? Well, we know that some data are available that we would need. We would need data for the 3 different possible sources of contamination in the notes that gives rise to Y. We know that contamination on notes from drug dealing, some of those data are available from previous drug trafficking trials. However, we don't know anything about contamination of drugs on banknotes of people who use drugs. And as far as I know, these data are not available, which would mean we'd have to collect these data, which would involve following people around who do drugs and trying to measure amount of contamination on their banknotes, which probably wouldn't be very well received. So that would be more difficult to collect. However, information on contamination of banknotes that are counted on a contaminated table could be done if experiments were specifically designed for this purpose. But currently these data are not available. So in order to figure out whether our model actually works and makes any sense, we made up some data based on prior knowledge about what these data would be expected to look like. And when we did this, we did this so that for each one of these different scenarios here, i.e. the rows in the table, are quite representative of what the different storylines are in our chain event graph. We've got where the notes traffic, whether they're heroin trafficking, for example, yes or no. Did the customer use heroin only or heroin and other drugs? Was the table contaminated with heroin and other drugs, or no drugs at all? For all of these different scenarios, we came up with some sensible parameter values that were used to evaluate what Y is and what Z is. Z's coming from a binomial distribution, so it only needs that parameter there. Then we've got information from the event transition probabilities, which were based on, again, our own particular expert elicitation about the system, which could be changed depending on whether more expertise can be gathered. But when we put all of this information into the model that I showed you before, we found that the log likelihood ratios were were as follows for each one of these different scenarios. And they're quite encouraging, because when we assume each of these rows is the truth, we're getting a log likelihood ratio that is supportive of either the prosecution being more supported or the defense being more supported when these are assumed to be actually the case and real data. So that was quite useful. But what can we conclude about this kind of work? Well, we tried to use Bayesian networks and we were coming along with some quite good results, but we found it difficult to include information, some expert information, in Bayesian networks. We also found it difficult to include a temporal aspect to the network. So we decided to try something a bit different and to look at these chain event graphs as an alternative. And we did that, and we found that they're quite helpful. They're very difficult to put together, was one thing that we found. You've really got to know the system or the case really well, but it's a very logical way of thinking about very complicated activity level propositions like that, because you can include lots of different evidence, you can think about the temporal structure of the case, and it's quite a logical way of thinking about these kind of problems. When it comes to making more applications of these, potentially chain event graphs could be useful when it comes to identifying areas where more experiments or more evidence is needed in a case. Potentially, it could even help lawyers or forensic scientists identify either weak or strong timelines that are being put forward. And we could find a way of deriving probabilities of different events, including different kinds of evidence in these complex cases. So I'd like to thank the following people for all their help, especially Amy and Jim, who've done so much with trying to get this project going. And thank you all very much for listening.
Thank you, Gail, for excellent timing. Again, do we have questions either in the chat or raising your hand or just unmuting? It occurs to me to wonder what response you get from the police when you suggest what experiments they might do. Is that several steps away from where you're at now?
Yes, I would think that's quite a bit away. I mean, we're more on the theoretical side, trying to develop this network and get it published. But yeah, that's a good point. I mean, I think Amy's done similar kind of experiments in the past, but it would be difficult to do specific ones when it comes to contamination of a table, because it kind of implies that correct procedures weren't followed in particular cases. So, but that's a good consideration.
Yeah, we did some of the initial work with a forensic science provider in Bristol, who were doing little bits of experimentation. So we have some small data sets from them. But yeah, it's a difficult one trying to get the data sets in place to answer all the questions you need to.
I suppose there's another statistical question in the background to that then, which is what are the more common types of crime and evidence, and therefore where would it be worth putting in the effort on such things? I think Peter's got a question. Peter?
Thank you. Thanks for the talk, Gail. I've got a couple of questions, actually. I'll just ask one of them, though. This is a slightly nerdy question about the interpretation of these chain event graphs. And I'm very familiar with Bayesian networks, and I understand the Markov properties that they enjoy. But I'm not sure exactly what the assumptions are underlying the chain event graph. I wonder if you could possibly go back to slide 24. Perhaps I could pose the question more acutely. 24, two more, that's it. Okay, so in the middle of the top, you see there's a probability eta of going from pound ks to s minus, and the same symbol eta goes from between the same two states further down the page in the other timeline. So how am I to understand that probability eta? Is that a conditional probability of s minus given pound ks, is it? But is it also conditional on all the preceding history of the nodes to the left of pound ks, or is it just conditional on the value of pound ks?
Yeah, this is something that we've thought about a lot when it comes to making these Bayesian networks. I think it's the latter, and it only depends on pound ks, but we can't, we did try and merge these probabilities together because they're both etas after pound ks. So they should be merged together according to the stage tree. But some of the probabilities downstream are different.
Yes,
so,
I know it's just to the left of there, you've got an epsilon and a zeta between two nodes that look the same. So I'm guessing they really are conditional on the whole past, which of course is fine, provided you respect that when you calculate with it.
Yeah, I think they're conditional on everything that comes before them, but we don't combine them because of the stuff that comes after them.
Right.
I'm not sure. I'm sure that we had a discussion with Jim about this before, but we weren't very certain about that. I mean, that's the trouble with these things. It's a lot in development, and so it's difficult to get to the heart of it sometimes.
Yeah, I mean, this is all part of the model building, but you've got to clearly understand when you're building such a model that what conditional probability is supposed to be going on that arrow. Otherwise you're just going to be going around in circles, I guess.
Yeah, we're just at the stage now of trying to put actual probabilities on things, which is proving tricky.
Right. Okay, thanks.
Peter, do you think there's one interpretation's more natural than the other?
Well, I don't know. I mean, I've hardly spent more than 10 minutes of my whole life thinking about chain event graphs. So I'm through it. I mean, it's obviously much more powerful if you can rely on all the past history when you're establishing conditional probability, except in that you can model more, a bigger variety of situations. But on the other hand, you've also got a lot more to think about when you're establishing conditional probabilities. And that also comes in if you're ever trying to infer values for those from experimental data, of course.
Yeah, so we had it's difficult when including all of the different event transition probabilities in the model as well, because on the face of it, it doesn't look as if it makes much difference, but actually it does when you think about it more carefully. And through the experiments, we found that it really does make a difference what these event transition probabilities are, particularly some versus others. So choosing those is quite a important stage as well when constructing this.
Mm-hmm. Yeah. Fascinating stuff. Thank you.
Do you have any other questions or comments? Jim?
Yes.
Jim Rothman?
Yes, what does it mean, looking at the same chart, if the probability of the defense storyline and the probability of the prosecution storyline add up to considerably less than 1?
Sorry, for this chain, for the event transition probabilities, you mean?
No, at the end.
Oh, sorry.
The ratio based upon the ratio of the two probabilities. But supposing those two probabilities are much less than add to something that's much less than 1. Supposing the defense storyline is say 0.5%, and but the prosecution storyline only works out at 10%. Do you conclude that there's 100 to 1 probability that the likelihood ratio is 100 to 1?
I mean, it depends very much on the parameter values that we're putting in yet. I mean, a lot of these are not confirmed. So
yeah, but I mean, if in a real situation you put in your parameter values and you have reasonable confidence in them, I understand that in your case you've had to guess them. But I mean, if I was guessing them, I would guess them in such a way as to make sure that the two probabilities added to 1. And maybe that's because I'm more of a cheat than you are.
Jim, isn't that similar to Therese's question about, are you sure your model is not just that you've got one that has a high,
Yeah, that's also how I understand it.
Yeah. What you're saying, your question is saying, one of the things you have to do is make sure that this whole model is well posed. It doesn't leave you with a glaring get-out clause about which somebody's never thought of.
Yeah.
But then I
Yes.
suppose that is the reality of a legal case. I mean, you know, it surely can't be impossible to think of a prosecution and a defense case being run when the actual truth was something quite different from either case.
Well, I mean, that's one of my worries. I don't see why the defense should have to put up a proposition.
So you mean that the prosecution would put forward a proposition and the defense would be the negative of that?
Exactly.
Yes, in this situation, we were following the truth of actually what happened in the Stephen Compton case. So our idea about the jewellery was what was written in the notes. What we embellished on slightly with the chain event graph was that we came forward with these two propositions that were put forward by the prosecution, because you could see how these propositions would follow one from the other. I mean, it's a lot of the time, happens quite a lot that people are accused of drug trafficking based on the same evidence. So we included these different hypotheses as well. But the two original, the prosecution's hypotheses and the defense hypotheses, were put forward in the real case. So we wanted to just kind of keep to what happened in reality so that we could defend our model more vigorously.
But you agree then that if you were asked to do the calculations in a real life case, you wouldn't do it on the basis of any defense proposition?
Possibly, but we haven't really thought about that eventuality. We kind of just stuck to the Stephen Compton case, but it could be that if the defense don't put forward a proposition, then they would have to think about that.
But even if the defense do put forward a proposition, is it your job to isn't it your job to assume, to look at the third possibility that neither of the two propositions are correct?
I guess it depends from whose perspective you're drawing the chain event graph. If you're doing it from the perspective of the judge who's being presented with the kind of stories on both sides, then you have something there to plug in. If you're the forensic scientist and you're trying to investigate the evidence, and yeah, maybe you do have a responsibility to look for other explanations.
I thought that was a responsibility. Isn't that part of the idea of an adversarial system? Is that it is the defense responsibility to offer alternative explanations?
Can I come in? It may be just in Scotland, of course. But in this case, the jury story was put forward voluntarily by the suspect, presumably.
Yeah, that's right.
But he shouldn't be limited by that. This is Jim's point. It's up to the the prosecution to prove that their story, you know, is the best explanation beyond reasonable doubt, or whatever term is used. If he feels obliged or is pressured to put forward an alternative story that's a weak one, right, then that shouldn't increase his chance of being convicted. Why should he know enough to put forward a strong one?
Well, I was going to say, shouldn't under what set of assumptions, Peter? Because, I mean, it's partly, I suppose, what I was thinking about. But if a person is innocent and can produce a truthful explanation, should one be factoring in the ground truth which we don't know when we're doing this? If a person is genuinely innocent and states exactly what happened, how likely is it that that will be sufficient? I mean, that's an open question.
Well,
Alan, what were you saying? The defense doesn't. You've unmuted. You want to say what you were? No, maybe. I mean, I suspect for this one would doubtless get input from lawyers working in jurisprudence.
I mean, evidently people are convicted without, are convicted under these circumstances.
Yes, I mean, you get both.
But should they be is another matter.
Yeah, well, I think, oh, sorry, I was just thinking the simple thing that clearly you get mistakes both ways. Innocent people convicted and guilty people who are not found guilty. I guess the question is how, in a sense that we're working on, is what is the best that we can contribute through our understanding to reduce the error rates.
Yeah, but I mean, I hesitate to base the whole RSS attitude to law on the Sally Clark case, but it's tempting in this case because, I mean, Sally Clark was convicted because, as it were, the defence story was incorrectly evaluated.
Yes, yeah.
But why did there have to be a defence story?
Why have we got an adversarial system? I mean, I don't know what would happen in, say, France or Germany or Sweden.
You know, as you know, I'm not a lawyer, but I thought the adversarial system means that they were fighting over the prosecution hypothesis, not that they were fighting between two different stories.
I'm not sure that my memory of the Sally Clark case was that the prosecution witness came up with was giving medical evidence, and he suddenly gave some statistical evidence which he wasn't qualified to do, and admittedly the Court of Appeal decided that hadn't influenced the jury. But I must say I've always been a bit skeptical about that. I would have thought the jury would have been influenced by that sort of argument, even if Meadows hadn't given this phony calculation or assumed independence of the two issues. But, and if anything, it was the fault of the defense. I mean, admittedly, you know, I'm saying it was the fault of the defense, but it isn't necessarily the defense's responsibility in these cases to give an alternative explanation. But that didn't arise. Here we've got a case where we've actually calculated, or not, I agree that it's all hypothetical at the moment, but it's proposed that we will actually calculate the probabilities of the prosecution case and the probabilities of the defense case. And we are arguing that the right thing to do is, having calculated those two probabilities separately, is to report the ratio or the log of the ratio between them. And I'm wondering whether that is the right thing to do, and wouldn't it be better perhaps to just state the probabilities of the prosecution case? And if that's low, then that's the end of it. If it is 50% or more, then at least you've got some evidence. But the defense case is irrelevant. You can say the prosecution case is 90. The explanation is not for the prosecution case is 90%. Then you do have a ratio of 9-to-1, a log ratio of 9-to-1.
I think, realizing, just having a look at the time, I think this is probably a conversation that will carry on for a few more decades.
Yeah.
But it's good to have it discussed and to have different contributions in both these cases from Gail and from Theresa. So I've forgotten what the convention is on online meetings for thanking people. I think quite a lot of people put a note in the chat, but I think we can all possibly unmute and show our applause in the old-fashioned way as well. So thank you very much. and to the questioners.
Thank you.
And the next meeting of the section is the 8th of February meeting on the use of algorithms to support human decision making. And there will be a paper for you to read, so I hope many of you will be able to attend that. Thank you.
Goodbye.
Good night.